Okay, so what was I saying? Right, we said we're not going to talk much about kinetics, but now we do talk a little bit about kinetics. We talked about the large activation energy asymptotics, the thermal flame theory, but of course this simple analysis is not true in a sense, because we know one-step reaction it doesn't reflect the true chemistry. The true chemistry, it lives off the radical balance and things like that. And here the only thing we have is an activation energy that has to do all the work of the nonlinearity that we have in flames. And so this is not true. But on the other hand, you could say, okay, why do I need this simple analysis? I could also do detailed kinetics. We had the equations. Let's just compute the burning velocity. But again, you can do that. You can compute burning velocities with some code that you get off the web and some mechanism that you get off the web. But you don't learn anything from it. It doesn't tell you anything about the physics. Here, contributes little to the understanding. So one thing I want you guys to take away from this is the value of analysis. Okay, today we can compute so many things very, very quickly. I mean, you can compute these burning velocities in seconds, really. But you don't understand. Just from doing that, you don't understand anything. You can compute ignition delay times in a matter of seconds. But you see it's very complicated, but just from computing it, you don't understand why things behave the way they do. Analysis, these analyses, they're not so accurate. They don't give you quantitatively exactly the right value, and we'll see this later on. But the one thing they do is they tell you how things work together. And so this is what we want to do now is we want to talk about this four-step chemical mechanism. This is one of the most important, I think, personally, one of the most important contributions in the last 30 years to combustion science, because it really shows us how does a flame work, in the inside. Okay, so this shows some computed profiles here of a flame. You see there's a methane flame. This here is temperature. You see this just like we sketched it. This is this exponential increase we saw earlier. And then, here it goes somehow to the adiabatic conditions. This is the H radical. You see it's 0 here in the preheat zone. And it goes up, has some maximum, and then goes to equilibrium here also. You see that this is again the temperature. You see that in the flame you form CO first, as we said earlier, and then the CO is converted to CO2. And then here, I can't remember what the conditions were, but here you see there's some CO left over, and then you have some CO2 here also. Okay, so so one of the problems is we said earlier, if you have multi-step kinetics, you have many species. You have many equations. The analysis is hopeless. I mean, it's really hard to do this kind of analysis we did earlier. If you have many species. We were only able to do this because you have a one-step reaction, which have only two species plus the temperature, and then we had coupling functions relating these to each other. We had one equation. Okay, so if you have like 2,500 reactions, you have 2,500 different timescales, 2,500 different processes. Each of these processes will create one layer, in the flame. It will impose a time scale and with, the flow or length scale somehow on the flame. And so the first step always is to reduce the mechanism to the smallest possible size. And here this is the four-step mechanism. Four-step mechanism is 4 steps. That's kind of the minimum you need, and we'll see on the next page why this is. But we'll also go back to, to understand what's going on, we'll also go to a 3-step and a 2-step. This here talks about stoichiometric methane air flames, but similar analysis has been carried out for lean flames, moderately rich flames, and also for very rich methane flames, and also has been carried out for other hydrocarbon flames, and so on. Okay, so we'll start out by developing this reduced mechanism first. We start out with a full methane chemistry. We keep, so for steady state assumption basically means you assume that the production of a species and the consumption of a species, they're very, very fast, okay? And they're much faster than the transport. And so then in the governing equation, all the transport terms on the left-hand side is 0. And so it basically means the overall chemical source term is 0, and that gives you an analytic expression for the steady state species. Okay? The non-steady state species for which you need to solve equations then, transport equations, are fuel, oxygen, water, CO2, H2, and CO, and in addition the H radical. The H radical is a radical, so actually it is produced very quick, very high rates and consumed at very high rates. And so the steady state assumption is not so bad actually for hydrogen, but we keep the hydrogen radical here in this mechanism to be able to see, what happens with the radicals. Just to have this as being one representative one of the important radicals. Okay, so this represents the competition then between chain branching and chain breaking reactions. Turns out the most important chain branching and chain breaking and chain branching reactions are these two reactions. I mentioned this before. The reaction H plus O2 goes to OH plus O. That's the most important chain branching reaction. One thing is important, you should remember this for your life, that's at least my way of thinking, is how many radicals are being produced in this reaction? 1F. 2 radicals. You produce 2 radicals, but you have one here on this side also, right? So the net production is 1 radical. No, I would say you were right the first time. It's 2 radicals. Why is it 2 radicals? Why do I say you produce 2 radicals? Yeah, OH and H are different. OH, O, and H. These are the 3 most important radicals. They do all the work. Everything else is just on the side. But they're different. Which one is different? There's one that's different. The O is different. O counts like 2 other radicals. O is very, very strong, very, very potent radical. So I always count O as 2 radicals. And so you see here on the left-hand side you have 1 radical. On the right-hand side you have 3 radicals, so you produce 2 radicals. Okay, if you do this. So this is chain branching. This is not very fast. It has an activation energy, but once it goes off, it really, you take 1 radical, you produce 2. Then you take the 2 radicals, you produce 4, and so on. No, sorry. You take 1, you produce 3, so you multiply it by a factor of 3, and you do this again, and so on. So there's very, very fast exponential growth. Okay? Now, when I say you have H and OH and O, some reactions here, they go with H, other reactions go with O, and so on. That's all not so important. You would think if you produce, let's say, an OH radical, and you have another reaction that needs an H radical, like methane plus H goes to methyl plus H2. Is that the same? Do you first need to do something else? Yes. You need to convert the OH into an H radical before you can do that. But these reactions are very, very fast. Okay? So don't worry about is this an H or an OH radical, because the interconversion between these radicals, O, OH, and H, is very, very fast. Okay? And it's fast in a way that they just go back and forth all the time, and between these 3 radicals, and it's such that you know, if you have O produces 2 of these other radicals and so on. So that's this. And then here we have the second one. This is actually, it doesn't look like that. You have H plus O2 goes to HO2. So you have one radical left and one radical right. It doesn't look like it does very much. But the question is what happens to HO2, and in flames, the HO2, it basically goes back to H2 plus O2, and so this takes radicals out. This is not, this here will, subsequently will take radicals out. So this is a very fast radical production step, very fast radical consumption step. Okay. This is interesting because these reactions, one produces radicals, the other consumes radicals. And I said the one is the most important radical production, the other one is the most important radical consumption. And I said the most important thing in flames, or in combustion in general, is the radical balance. It's interesting because these reactions, they look very, very similarly. Okay? So what we can do is, you know, define this, we call crossover temperature. Now, remember when earlier on, we were talking about the, the coupling functions. And I said, this is the most important thing, okay? It was not true. Coupling function is very important. The most important thing is the crossover temperature. Understand the crossover temperature and the coupling function. But understand the crossover temperature and your life is saved, okay? So everyone take a deep breath and then we talk about it. Again, it's a very, very simple concept, but you know, it's very powerful. It will teach you a lot if you understand this. Maybe you know this already, but if you understand, it teach you a lot. Okay, take a deep breath and then we'll look at it. So we have two reactions. One produces radicals, one consumes radicals. You could just say, so we call this here 1 and 5, okay? If 1 is faster than 5, then things will go off, okay? Then you have chain branching, exponential growth of radicals, explosion, whatever, okay? If 5 is faster than 1, then you take out radicals. The net effect is chain breaking. What happens to a flame? It will just extinguish. It will go out, okay? So the two options you have, you compare these two reaction rates to each other. If this one is faster, you get explosion and everything, you know, goes bam. Or the other one is faster, the flame goes out. These are your two choices, okay? Now, and this is the part that's interesting, and that what makes our life really easy. Because these look very, very similarly, it's very easy to compare these two rates, okay? So, the reaction rate of this first reaction here is K1 times the concentration of O2 times the concentration of H. The concentration of 5 is K5 times the concentration of O2 times the concentration of H times the concentration of this third body. Concentration of third body, you can say, is the overall concentration. Let's say this is just P over RT. Okay, so Cm. Cm is the overall concentration. Is P over RT. Okay? So, taking the ratio of these two, that means then if the ratio is larger than 1, explosion, chain branching, whatever. If the ratio is smaller than 1, extinction. Okay, simple. So I take the ratio of these, and now this is the beauty of this whole thing. You see CO2, the concentration of O2 and the concentration of H, they're both in the numerator and in the denominator. So all of this is a few slides later. I think I just put it here a little more prominent because it's such an important thing. It was explained just a little bit on the side. So I can cancel these out, and the ratio is K1 over K5 times Cm. Okay? And you see, these K1, K5, they're only function of temperature. They're, you know, just these Arrhenius coefficients. And Cm here is function of pressure and temperature. So this ratio is just function of pressure and temperature. And again, so from this then, I can say, okay, so if it's larger than 1, I get this. If it's smaller than 1, is that. So let's compute the temperature where this is exactly equal to 1. Okay? And that's the crossover temperature. If temperature is lower than this, then 5 is faster, extinction. Temperature is higher than the crossover temperature, then 1 is faster, chain branching. Okay? So you see this here gives you an implicit, I mean these are exponential functions, but this gives you an implicit relation here for this what's called the crossover temperature, or later on we'll also call this the inner layer temperature. It's the same thing. Okay, so but we can do this graphically also. This would be an Arrhenius plot here for reaction 1. Reaction 1 has a relatively large activation energy. You see this is a function of pressure. You also, let's just use 1 atmosphere. Then this here is independent of pressure anyways. And then this line here, that would be K5 times M. So K5 times M is this line. So for pressure of 1 bar, that's what it is. And you see where these two cross, that's where the crossover temperature is. For higher temperature, so it's an Arrhenius plot, higher temperatures to your left. Higher temperature, the chain branching gets faster. Lower temperature, chain breaking gets fast. Okay? So what we said earlier, there's an ignition temperature, and the thermal flame theory, you know, it just means you go, if your temperature is small enough, then the reactions become slow. Here, if you consider multi-step chemistry, there's a very, very distinct temperature that lets things burn or not. So why does this thing not burn? Because the temperature is less than the inner layer temperature, less than the crossover temperature. And any radical you form from this thing, it will go away immediately, okay? Because of this reaction 5, okay? Which even at room temperature, you see, at room temperature is very, very fast. If you increase the pressure, then you see the concentration changes. This line moves up, and you see the crossover temperature will be higher also. Okay, so it's easier to extinguish a flame at high pressure. Okay, so this is what we said. So this is very, very important, crossover temperature. This is what these two reactions do. So let's see how we, what happens with these reactions. This here is reaction 1. H plus O2 goes to OH plus O. We want to derive now a reduced mechanism. I said there are actually 3 reactions. They're called the fast shuffle reactions. And these reactions do nothing else than converting O into OH into O. They just, you know, keep these kind of in partial equilibrium. And this is 1. H2 plus O goes to OH plus H. This goes back and forth very, very quickly. And you see I have 2 radicals here on the right. The O radical on the left. Standard textbook, you would find that this is a chain branching reaction, because standard combustion textbooks, or many standard combustion textbooks, they say, okay, I have 1 radical here, 2 radicals here. But you know, my world, this is not right, because these go back and forth very quickly. What does that mean? You have chain breaking and chain branching all the time. Really what this is you have, this counts as 2 radicals, this counts as 1, this is just a chain propagating. It goes back and forth and it doesn't do anything, okay? Same with this one here, H2 plus OH goes to H2O plus H. You see this goes back and forth very quickly and just converts an OH into an H radical. Now, because these happen so fast, we can just say they happen instantaneously, and this O will immediately convert it into an OH and an H. And then these 2 OHs, they will be immediately converted into an H. And so we reduce everything back to the H radical, which is a part of our system. So if we add all these up, then we have this global reaction step O2 plus 3H2 go to 2H2O plus 2H. Okay? This is now a global reaction step, which is written just in terms of the species, the non-steady state species we keep in the system. And it shows you and it's the result of this reaction here. The net result of this reaction is that you take the O2 and the H2 and you produce two radicals. Okay? And the rate of this overall step, we can say, because these reactions here, we now, for the sake of this analysis, we assume these are infinitely fast, and so the rate of this is the same as the rate of this slow initiation step. Okay? So that's our reaction number 3. This is the chain branching. Now reaction number 4, H plus O2 plus M goes to HO2 plus M. I mentioned this earlier. HO2 goes with H to H2 plus O2. That's how it's consumed in a flame. For ignition processes, this is different. Sometimes this can be very helpful. But here that's what it is. And we say this here is again a very fast reaction. This here is the slow reaction. And so if I add these up, I get H plus M goes to H2 plus M. And you see I take two radicals and I convert them into no radical. Okay? Again, because this is the slow chain initiation or the initiation step of this path, the overall rate of this would be the rate of the initiation. Okay? So this is these are the two global steps, interestingly, that don't depend on any hydrocarbon chemistry, and they're the same for any hydrocarbon fuel and for hydrogen. Okay? So the main chain breaking and the main chain branching, they're independent of what fuel you have. Okay? It's always these two. Good, so now we talk about methane, and so methane needs to be consumed somehow, and the main methane consumption step is methane plus H goes to methyl plus H2. That is here a relatively slow step, and we say all the steps that follow, they're very, very fast. And now the question is, how do you know which step is the step that consumes methyl radical? How do you know? Well, you know from just doing detailed calculation. You do detailed calculation, so detailed calculation is good for something. I said earlier, analysis is very important also, but detailed calculation is good for something also. So you can do a detailed calculation of a flame, you look which ones are the most important reactions, and now you just take the most important one and you forget about the others. Okay? So, this forms a methyl radical. Turns out the methyl radical is consumed mostly with the O radical to form formaldehyde plus H. Formaldehyde goes to this HCO species here. This HCO just decomposes into CO plus H. And then, so that's what it is. Now we have formed CO. And you see we have O here, so we want to convert this radical, we want to convert all the radicals back to H radical. And so we just add these two steps, which are also very fast. And if you just add the left and the right sides up, you cancel out with, what's both on the left and the right. This is what you get. Methane plus 2H plus water goes to CO plus 4H2. Two things are interesting. Number one, this is what we said earlier, when you consume fuel, you convert it to CO and H2. Okay, this is what we knew earlier. And then the consumption of CO, and this goes fast, let's say, and then the consumption of CO, that's slow again. That's a slow step to form CO2. Okay, so that's number one. But the other thing that's very interesting here is the consumption of the fuel consumes radicals. You see this? If you want to convert a 1-methane molecule to CO and H2, you have to use 2 radicals for that. This is very, very expensive in terms of flame chemistry currency. This radicals, this flame chemistry currency. Remember earlier we said the path through the C1 chain is slow. This is why. The path through the C1 chain, and this is the culprit here, the methyl radical is very stable, is a radical, but it's a very stable radical. In order to consume this, you have to use something very, very powerful. So you see you have 3 radicals here on the left side, you have only 1 radical on the right side, so you consume 2 radicals in this step. That's the reason why you need so much. Now the alternative to this step here would be 2 methyl go to C2H6, and then the T2H6 consumption, that's pretty much goes without using up radicals, and then you don't get, I mean, if you go to the C2 chain, you don't have these radicals here. But here we neglected the C2 chain, and so this is what we get. Okay? So again, analysis tells you a lot. I mean, simplification tells you a lot about the real, the important processes. Okay, this is what we call step number 1, and then what do we have left is the CO and the H2, and so let's see what happens to CO is the oxidation. The main consumption of CO is oxidation with OH. CO plus OH goes to CO2 plus H. And so now here we have OH. We want to convert it back with this very fast shuffle reaction back to H. And then you see you get the CO plus H2O goes to CO2 plus H2. This is the so-called water gas shift reaction. And we talked about this earlier. Okay, so we put this all together. These are our 4 steps. We have one that consumes the fuel and forms CO. We have one that converts the CO into CO2. And then we have a chain breaking step and a chain branching step. And this is the main combustion physics that you have in a flame. Okay? Now you can imagine each one of these steps now. Earlier, we had like maybe 100 different reactions, so we had 100 time scales. Now we reduced this down to 4 reactions. Okay? Now we have only 4 time scales. Problem is easier. It's easier to analyze now. Okay, so this summarizes this. We have these 4 steps. We said the rate determining step is always the initiation step. So the reaction rate of this global step number 1 would be the reaction rate of this. The water gas shift reaction would be this reaction rate, and so on. This is what we said earlier. Okay, so that now, if you would do a real systematic reduction, you would not neglect, the reaction rate of all the rates that I said are infinitely fast, so you get more complicated reactions. But these are what we call the principal rates. This is in the first order approximation, this would be correct. Okay? Good. So now what's interesting is you have these reaction rates of these, and you see there's a concentration here of OH, and there's a concentration of OH here basically, which you want to get rid of. So these reactions here, 2 and 3, they can be used now also. We said these are very, very fast, so we want to say they're in partial equilibrium, meaning forward rate, reverse rate are the same. And if we say forward rate and reverse rate are the same, then you get a partial equilibrium condition here for this in terms of H, OH, and H2. And so this is given in terms of the equilibrium. I'm not sure if this is clear exactly how this works. So you have, let's say take this reaction here. What is this reaction? So it's O plus H2. So you have, we want to say the forward rate. What is this? W2 F forward should be equal to W2 reverse. Okay? And so this would be K2F times concentration of, what is this, O and H2? O times concentration of H2, and then that should be equal to K2B times concentration of OH and H. Concentration of OH and concentration of H. And this means now you can say CO times CH2 divided by COH times CH, that is equal to K, what is it? Put this 2B divided by K 2F, 2F. Okay? But this here, so if we say these are in equilibrium, remember, this here was nothing else than the equilibrium constant. Okay? This was what we called the Kp. So I can write this also in terms of partial pressure. It's the same thing. Okay? So this is the Kp. So Kp really is the ratio of forward and reverse reaction. Okay, so this is 1 over Kp, actually. Kp is a forward divided by reverse reaction. Okay, so so you see now I can. So this here is just thermodynamics, right? You can compute it just from the thermodynamic properties, and then I can write CO as function of these 3 times this equilibrium constant. By the way, just in case you don't know this, this is also how a chemistry code would compute reverse reactions. You provide just a forward reaction, and then you compute in the code, you compute just from thermodynamic data, you compute this, and that gives you the reverse reaction. Okay? So, so we get these partial equilibrium assumptions that depend on K2 and K3, and then these are the reaction rates, forward and reverse, considered here for each of these reactions, or at least for this reaction 9 and reaction 1. And these are the equilibrium constants that are missing here. And so you see this is now the 4-step mechanism gives us these reactions. It gives you for each of the reaction rates. And the reaction rates are expressed only in terms of the species that you solve for. So this is a closed system. You can use this to do flame calculations. Okay? Okay, so this is the 4-step mechanism, and it, taught us all these things that we just discussed. We want to reduce this further into a 3-step mechanism. The way we do this is we want to set the H radical to steady state. Why do we want to do this? Because we will get a steady state relation, an algebraic relation for H. And that would tell us something about what happens with the H radical. Okay? That's the only reason why we do it. Here we have an equation for H, and it has, all these reaction rates and so on. It doesn't tell us very much. These are so if we want to further reduce this, then we can assume that H radical is in steady state, and we add reaction 4 to reaction 1 and reaction 3 of the earlier mechanism, and then this is what we get. And the rates of these stay the same. Okay, so you see this just eliminated by adding these reactions to each other. It eliminates the H radical. So from that, then we also get a steady state relation for the H radical, because if you look back at the original mechanism, you can say the L operator here is transport. It's a time-dependent term, convection term, and all of these things. And on the right-hand side, you have the reaction term. And if you look at, again, if you look at this mechanism, then you see the reaction rate is minus 2 times W1, minus 2 times W3, plus 2 times W4. Okay, that would be the reaction rate for the H radical. That's shown here, where the factor of 2 is skipped. So if this is 0, then you can equate these, and from this you get this relation. So if I just plug in all the reaction rates, I can solve this for the H radical. Okay, that's my steady state relation. So this is how this looks like. H is equal to some value here. Just say this is some constant, whatever. It's called here H equilibrium. And then times 1 minus this minus this. Now this first one here, we know what is this. This is the ratio of K1 and K5. This is exactly the whole thing, crossover temperature thing we discussed before. You already know temperature larger than the crossover temperature. This will be smaller than 1. Temperature smaller than the crossover temperature, this will be larger than 1. Okay? Interesting is, though, you have the square root here. So larger than 1 shouldn't happen, really. Or at least not much larger than 1. I mean, you also have this thing here, but shouldn't be much larger than 1. So Right, so if we look at this, this shows an interesting structure because at temperatures of 1400 Kelvin or above, the second term here in the brackets is small, and it has to be small because so it's small, but K11 over K1, this is something we can just evaluate, it's just temperature function, that is very large. Okay, but the overall term, it has to be small, otherwise you wouldn't have radicals, or this would become negative square root of a negative value or whatever. So for large temperatures, this has to go to 0. The only way it can go to 0, let's say for lean flames, is if methane goes to 0. Okay? So we see from this that in the reaction zone where you have radicals, as long as you have radicals, methane has to be 0. The other thing you see is now if you go to lower temperatures, then you see that this thing becomes large. If you are below the inner layer temperature, this thing becomes very large, and at the same time the radicals need to go away. So if this becomes large, the radicals do go away, and this shows again that basically the H radical and methane, they can't coexist. Okay, you either have methane or you have H. And if you think about it, the way this works is you form the radicals in the reaction zone, and then you have the methane diffusing into the reaction zone. And as soon as they come together, the methane is consumed. Okay, so both go to 0 at the same time. Okay, that's kind of what you can see from this thing. So now this shows again this inner layer temperature, and the inner layer temperature here, I mean the way we define it, it just assumes that all radicals are consumed just by this reaction 5. This is of course not the case. There are other reactions that also consume the radicals, like the whole fuel consumption also consumes radicals, is not considered here. So this estimation here for this inner layer temperature is an estimate, and maybe it's not exactly right, quantitatively exactly right, but it's a good estimate. And you see here is about 1050 Kelvin for 1 atmosphere. And so if we look at what happens here in the real flame at 1050 Kelvin, so this is a detailed chemistry calculation, 1050 Kelvin, this red here is the temperature. In the dashed line here is H radical, and you see it's exactly where the H radical goes away. Okay? It's exactly where the H radical goes to 0. Now I missed to, I should do this next time maybe, I missed to put in the methane, but methane also should go away exactly at the same point, yeah. Okay? Because they can't coexist. Okay, so that's what, so the only reason now I said we do this 3-step, 2-step mechanism because there's something interesting happening. The only reason why we looked at this was to get the steady state relation and to kind of understand how do methane and H radical interact and so on. Okay, so then we can go one step further. We can go to a 2-step mechanism. And the 2-step mechanism, now you can't set anything steady state anymore, but the assumption here is that you say, well, anytime the fuel is consumed, it forms certain amounts of CO and H2. And so I just take CO and H2, I take that as one coupled species, okay, in the right amount. So you see here, there is this H2 plus alpha CO. This here appears like one single species, okay? So these are coupled, which is why you get rid of the CO oxidation, and then you get to a 2-step mechanism. And the reason why you want to use a 2-step mechanism is because then, again, the asymptotic analysis gets simpler. And now, earlier we had 1-step mechanism in the thermal flame theory, and we had two different regions, the preheat region and the reaction zone, and then also equilibrium region, but that was not very important. And here we have 2 reactions, so we get 3 regions. One is the preheat region, it's chemically inert. The preheat region, now we can define this temperature, ignition temperature, very, very accurately. We say this is now the crossover temperature, And at the crossover temperature, this is where you form radicals, and this is where you consume, because of this, where you consume CH4. So we call this the reaction zone, or the inner layer. This is the inner layer of the flame. It's very thin, and because it's very thin, you can assume that the temperature in this inner layer is basically the crossover temperature. That's why we call the crossover temperature also the inner layer temperature. Okay? So that's the reaction zone, basically, or the inner layer of the reaction zone. And there's a second part here to the reaction zone, which is the oxidation layer, which converts CO to CO2. This is in the second step here. Okay, so this converts CO to CO2. So the assumption here, or that's how it comes out at the end. The preheat zone is very large. We say it's order 1. This order 1 means it's the order of the entire flame thickness. So you can say basically the preheat zone is the flame thickness. And then there is the oxidation layer. That is, in terms of the chemistry, is a very large layer, or very wide layer, because the CO to CO2 oxidation is relatively slow. And so this, we say this is order epsilon. Epsilon is much smaller than 1. But at the same time, this oxidation layer is much larger than the inner layer, which we say is of order delta. So delta is much, much smaller than epsilon. Okay, this is how these come together. Okay? So basically, look at this is the preheat zone. And then the oxidation layer is like this. Okay, so the whole flame is basically like the oxidation layer. And then if you zoom in the oxidation layer, then this is the oxidation layer, and then here you have the inner layer is very small. So basically, the whole reaction zone is basically the oxidation layer, is the width of the oxidation layer. And then the inner layer, that's a very thin layer, which does what we said earlier. Okay, so, details. If you don't have enough with, what was the earlier one we looked at? There was some detailed something of 25 pages. So here, if that's not enough, look at the analysis here of this. Just a few pages of going back and forth, and then at the end of the day, this is the result you get. Okay? And this result now, it is actually, in a sense, you see it's quite similar to the thermal flame theory, although it's different. So what's similar is that, again, you get these you have this TB minus T naught here. So earlier it was TB minus TU. We said the same thing. Here's just written in non-dimensional form. You have the lambda over Cp. You have this here. This was our diffusion coefficient. And then there's a lot of stuff here that involves the chemistry. And maybe also here's some Lewis numbers. Now, you see this involves the inner layer temperature. The inner layer temperature here is computed with considering the radical consumption in this reaction 5, H plus O2 plus M, but also in reaction 11, which is the fuel consumption. Okay? And so this is why it's a little different. There's an implicit relation here. But so this here gives you the inner layer temperature as function of pressure. And then this here gives you SL as function of inner layer temperature. So what you can do is you fix the pressure. Let's say here 1 bar, 1 atmosphere. And then with the second equation, you can compute the inner layer temperature. Here maybe 1400 Kelvin. And then with this equation, given the inner layer temperature, you can compute SL, which here is now for stoichiometric conditions is 54 centimeter per second. This is much higher than reality is less than 40. But we can say this is not so bad, actually. I mean, this is at least the right order of magnitude. And so this is not for giving us quantitative values for burning velocity. It's more to, tell us these dependencies. And we'll see that we can do some interesting things with these dependencies also. Okay, one thing that's interesting here is that this whole thing, the whole analysis, only has these 3 reaction rates. Reaction rate here, the chain branching reaction, the chain breaking reaction, and then this fuel consumption reaction. That's an interesting fact here. And another thing that's quite interesting is that you see T naught is basically fixed. It's independent of the chemistry. T0 is, or independent of the composition, whatever. We said earlier T naught is only a temperature function, or it depends on temperature, it's only a function of the pressure. You fix the pressure, you have the T naught, okay? It doesn't depend on the composition of your gases or whatever, okay? So to fix the pressure, T naught is fixed. But now if you dilute your mixture or you make it more lean, then TB gets smaller, okay? You can dilute this so much that TB is equal to T naught, okay? And if that happens, then SL is equal to 0. Isn't that interesting? See, earlier in the thermal flame theory, whatever you do, you can make SL smaller, 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 but you can never make it 0. Okay? Except you have no fuel. Okay? YF is 0, burning velocity is 0. As long as you have fuel or whatever, the reactants, you can't make it 0. And that is because, it's just this thermal effect. But here, you see a kinetic effect. As soon as you dilute this enough, this is equal to T naught, then chain breaking becomes fast, the whole flame extinguishes, and SL is 0. So that's one interesting outcome of this, and this maybe could explain flammability limits. This explains why you can't have a burning velocity for equivalence ratio smaller than some critical value. Okay? Okay, so we can now compare the result we got here and the result we got from the thermal flame theory. There are some details here about this, which I want to skip. And just here at the end, I want to say what the main difference is. In the one-step model, you see that the reaction zone thickness was of the order of the inverse of the Zeldovich number. That's what we found in the analysis. And in the two-step model here, it turns out that the oxidation layer thickness is of the order of the inverse of the Zeldovich number. And that makes a lot of sense, actually. But it just shows that essentially what you see as reaction zone as a thermal flame theory, that in reality is really the oxidation layer. Okay? And so you don't, as we said earlier, the oxidation layer is quite large compared to the inner layer. And so in the thermal flame theory, you just don't resolve the inner layer. Inner layer, of course not, because the inner layer really is governed. I mean, the oxidation layer is just an oxidation step. It's like, fuel or CO plus O2 goes to CO2. But the inner layer, that's really the competition for the radicals. Different reactions compete for the radicals. And that's what's in the inner layer. And so thermal flame theory doesn't know anything about inner layer, but it knows something about the oxidation layer. Okay, so this is what the thermal flame theory can do and what it cannot do. Okay, so maybe we should just look at this real quick. This is something you can do. This is interesting. Many people use this, which is why we have it here. Now, let's say you have a computer code and you want to compute a premix combustion process. Okay, and we saw earlier, maybe you need as an input parameter, you need the burning velocity. But the burning velocity is a function of space, time, the burning velocity is a function of equivalence ratio, temperature, pressure, and all of these things. And so you need a big table or something like this. But it would be nice also to fit the burning velocity. Okay, just fit it in with some fit function, and then you can just use the fit function for whatever fuel you want. The problem with fitting always is, we said here everything is very nonlinear. If you want to fit something that's very nonlinear, usually a fit is not very accurate, okay? But if you have the right basis function to do the fit, then it can be very accurate, okay? So I give you an example. So let's say you have an exponential function. It looks like this. And you want to fit this. You fit it with a linear approximation is bad, okay? Fit it with a polynomial is bad also, because the exponential is just, it's not a polynomial, it's an exponential, okay? So, but what if instead of, no, I mean, the exponential is bad. The exponential, that's the worst function in the world, right? I mean, it just, the derivative of this thing is still an exponential function. Okay, so that's, take any polynomial, infinite order, not infinite order, less than infinite, okay? But you take enough derivatives, it's zero, okay? This thing always, I have respect, you know, the exponential function. Okay, exponential function. Now, how can you beat the exponential function? What if you take the ln of this? Take the ln of this. It looks like this. Okay? Exponential of ln of exponential of x is x, right? Take the ln of this and now fit that function. Okay? So I call ln of my function, I call this g. Okay, I fit g, and then in my code I just take, you know, exponential g, whatever. So if you have the right basis function, that's what I'm saying. So this, of course, is just a linear function, very, very easy to fit, and exact and very accurate and all that. If you have the right basis function, then you can do a very accurate fit. Okay? So this is what we do here now. We have an analytic expression for the burning velocity. What if we just take that as a basis function for a fit? Okay? Very simple. So, see, this is our analytic relation here. This is our basis function for a fit. Okay? You see it's the same. Y fuel, there's some function here of temperature, which is all these rates. Okay? All the rate expressions. And then there is a T u over T naught times Tb minus T naught to the fourth power, and we just say this to the nth power here. Okay? So we use this as a, but also we have T naught here, we have Tb and all these things. Okay, now we have A and also this here. This here is just, we call this P. Okay? So we need to have expressions here for A and P, and then you see these M and N coefficients here, m equal to 1/2, that would be the analytic solution, n equal to 2, that would be the analytic solution, and so on. And so if you, so first of all, we say T naught is just temperature function, it's just function of pressure, but we see here is also function of the equivalence ratio, and that's because the fuel consumption also has an effect, but still we just model this as a function. This is an approximation. We model this just function of the pressure. And then we have these, we said A all has these kinetic rates. So we say A should be fitted as an exponential function because it has these kinetic rates. As function of T naught because that's the most important temperature in the inner layer. And then here, this also depends on kinetic rates, so we do the same here. So now we have this F and G and B and E and N and M. These are just parameters. Now we can do a lot of simulations here. You see here, let's say 1,000 simulations for different fuels. And then we can, you know, for different temperatures, pressures, equivalence ratio. And we can just, you know, determine these parameters by least squares approximation. determine these parameters, FG and so on. And it can be tabulated here. Okay? And then you can use these in your fit. And if you evaluate the fit, this is what you get. Here, this is just one example for methane. For other fuels, you get something similar, different pressures, equivalence ratio. This is all done just for lean flames because the analysis was for lean to stoichiometric flames. And so on. Interesting is then you can compare these M and N to the values we had earlier. This here is very close to 0.5, so that just says the analysis is not so bad we did. This here is also close to 2. This is also not so bad. But you see these other fuels here, acetylene. This M here is much larger. It's about twice this. And then also here, these values. So these values here, they're usually the same. But this parameter here, that changes for different fuels. And it turns out that acetylene here has a very large, comparably, a very large burning velocity. And, it just shows that the analysis, the way we did it for methane, there's something that's different for acetylene. So this also shows us for which fuels one would have to look maybe a little more closely again to look at the flame structure. But any analysis you do, you will always have the same not the same, but equivalent 4 reactions in this 4-step mechanism. For all of these, you can do a 4-step mechanism. The chain branching, chain breaking, they're exactly the same. CO oxidation will be exactly the same. And you have one fuel-dependent fuel consumption step. You would see that consumption of acetylene then is not radical consuming or so. Okay, so this we discussed. This here is same thing just for different pressures. This is a different fuel also. And you see is not so bad. Right. Okay, so what's the time now? Okay, so it's 10 past. Lilian asked us to stop 5 minutes earlier. We have like 5 slides or so. We want to stop to be sure we get in time to the photo shoot. Everyone's very nervous about this. And so maybe stop here. We'll do this tomorrow. Basically, what we'll see is that flammability limits, as I mentioned earlier, TB just goes to T0, and that's where the flame stops burning. So we'll continue then tomorrow. Have a good day.